let me introduce Hui. She is really a rising star in the area of machine learning and systems. She is an assistant professor in the College of Information and Computer Science at the University of Massachusetts Amherst. And she received her PhD from North Carolina State. And at Amherst, she leads a group that investigates these boundary topics between machine learning and systems. The reason why we invited Hui was that we realized that her group has been very productive in the last 12 months and has frequently used Flower to produce top-tier machine learning publications. So she and her team has invented methods called Flow and Flash as two examples of things that they've produced that appeared at ICML and iClear. And then to do this research, they use Flower. And so for that reason, we wanted to invite her to attend. Unfortunately, she couldn't make it here physically, but we really wanted to hear where she was going next with this line of work and where she generally thought the space of federated learning was taking us. And so we wanted to invite her. So that is an introduction. I really want to thank Hui for being here and talking to us all. Thank you very much for joining us today.
Well, I suppose this is the time I take over.
Yes, please.
Yes. Okay. Yeah. So I do hope that I can physically visit London, but yeah, we will do next time. So this work is done by my amazing PhD student, Kunjo. You can see her picture here too. I hope I also look exactly as the picture several years ago. So Kunjo was also here to make sure that I'm going to do a great job explaining the work. So before I start to present the work, because the work itself uses the setting of cross-device federated learning. So let me first refresh this concept for you. In the cross-device federated learning, you have a server, and the server hosts a global model, and you also have a set of clients. And these clients are willing to do all the hard work of training a machine learning model because they do not like to share their data to the server. And in one round of federated learning training, server will send a global model to a few selected clients, and clients will train the global model and then send the updated global model parameters to the server. The server do the aggregation of the model and prepare for the next round. So there are some general assumptions in cross-device federated learning. For example, you can assume that even though you will have a lot of clients, but only a fraction of the clients is going to be available for training the models. And each of the clients are likely to take part only once or a few times, and they may not like to actually store some of the states. You also have very limited sample counts on each of the device or each of the clients. So that's roughly about 50 to 400 amounts of data. And now let's look at the number one enemy for cross-device federated learning. That is data heterogeneity. Assume that the blue dot represents a global model from a previous federated learning round. And then after a client updates the model, the new model is represented in the green circle. If the data are homogeneous across clients, then the other clients would move the global model in a kind of similar way. And then after the server do the aggregation, the global model, that is the yellow circle, that will make everyone happy. However, when the data are actually heterogeneous across clients, some of the clients who are more unique will not really benefit from the aggregated model and thus has a very worse performance. The data heterogeneity issue can even change across time. Suppose each of the clients has their current local data and they work hard to make sure that the model converge. However, the local data on the clients could change over time. Then gradually, some of the clients that has very different local data would also suffer from the poor model performance. So we call this the concept drift in the client. In this talk, we're going to introduce two of our recent work. One tackled the problem of data heterogeneity across clients, and the other one is to further consider data heterogeneity across time. Specifically for Flow, we introduce per instance personalization and can boost the accuracy of the clients by up to 4.5 times %. And then the other work, Flash, which propose a server-side drift-aware optimizer, and it can achieve faster drift recovery. So let's start with the first one. So manual work has been proposed to handle cross-client data heterogeneity, and the way it works is to personalize the global model for each of the client. So Flow is motivated by the limited performance improvement from existing approach. So what we observe is that not all the clients can benefit from personalization. So the plot we show here show the x-axis are different personalization methods. The y-axis are the number of clients who do not benefit from the personalization. That means the personalized model actually achieve worse accuracy compared with the global model. We can see that up to 30% of the participating clients can see a performance drop even after personalization. But with Flow, we can decrease this percentage of harmed clients to 7% for this particular data set. And then another motivation is if we notice that even for the clients who do benefit from personalized model, not all the instance that sits on that client actually prefer a personalized model. So again, in this figure, the x-axis shows the personalization measure, the y-axis shows the percentage of the instance that can be correctly classified by both personalized model and also the global model, or only the global model or only the personalized model. So with Flow, we are able to actually boost the number of clients for all the categories and decrease the number of clients that benefits for only global model. So our goal in Flow is to try to get a personalized model which can process each of the instance and then let it propagate through either the global or the local model layers, depending on which layer is expected to fit the instance better to overcome the aforementioned issues. So this is achieved by a policy model which acts as the decision maker for each of the instance to pick between the global and the local parameters. If we expand even further, we have this policy module is divided by base and exit module. The base module will take the instance as the input and then output intermediate representation for early exit and attached to the base policy module. The exit corresponding to the layers of the global and the local model. So we derive this local model by doing the fine-tuning of the global model, and then we start to do the training of the policy and also the global model parameters alternatively so that we can dynamically route each of the instance on the client. We show some of the results here. It's using LSTM, which is a recurrent neural network on Shakespeare for next character recognition, next character prediction. And the x-axis shows the federated learning rounds, and the y-axis shows the validation accuracy on each of the client. We can see that Flow can achieve much higher personalized accuracy over the best performing baselines. And if we further look at the behavior of the routing decisions for each of the instance on a client, we can see that they actually fall into three categories. That is, the instance preferred or routed to only the global model layers, or the instance routed to only the personalized model layers, or both of them. So we realize that for the instance that do prefer to get classified using the global model, the routing parameters are more likely to pick the global routes, shown as the yellow. And then if the instance prefers the personalized model, the routing parameters do pick the local model routes more likely. And then for instance that can be classified by both, then the routing policy still prefers the global model because of our training mechanism. So the main takeaway from this first work is per instance personalization can help improve the data, like improve the performance of the model under data heterogeneity. And then the main insight is to have a dynamic personalized model instead of our static ones. And then it can help improve the accuracy on the clients by up to 4.6%. So The previous work has been looking at what kind of models that a client side can train in order to handle data heterogeneity. In the second work, we look at how can the server side help with the data heterogeneity, and particularly how can the server side help with the concept drift combined with data heterogeneity. So just to address heterogeneity across clients, there has been some work proposing adaptive optimization that can be done on the server side to address data heterogeneity issues. The way it works is you have these gradients, and you keep track of the gradients statistics, and so if we use the delta t to represent the gradients, and then it will keep track of our second momentum of these gradients, as denoted as a VT in this equation. And then to update the model parameters in the global model, we use the previous model weights and then plus the first momentum and then scaled with an effective learning rate. So this effective learning rate is, it has a learning rate and then divided by the square root of the second momentum. And then we get a new updated model weights. So this is typically how adaptive optimizer work. So, but we realize that although adaptive optimizer are very effective in handle data heterogeneity across client, but it can be very slow to adapt to the drift that is across time heterogeneity. The plot below shows the accuracy curve during federated learning, and at the onset of a drift, an existing approach, Federated, that is adaptive optimizer, can take a while to recover from the drift. So that is a Federated, and the H is the yellow curve. And then if we do not use adaptive optimizer, the performance is going to be even worse. That is the purple line. So that is the Fed average. And you can see that even without drift, the accuracy is by no means that is as comparable as accuracy from adaptive optimizer. So the lesson is adaptive optimizer do help with data heterogeneity, but it is very limited in handling concept drift. So we find the reason that adaptive optimizer cannot actually adapt to the drift fast is because its effective learning rate is relatively small, even when the drift happens. So Flash instead tries to increase or try to modulate this term, and so that we can make it drift aware, such that when a drift is detected, effective learning rate can increase so that we can accelerate drift adaptation. The core insight in Flash is we find that the difference between the squared gradients and the second momentum of the gradients aligns very well with the drifts. So we call this a gradient disparity. The plot on the left shows how gradient disparity will change with the number of rounds in federated learning, and also how does it change if the drift start to happen. So without drift, the gradient disparity becomes smaller and smaller as the training converges. However, when there are drift happen, the gradient disparity goes up. So our basic idea is to use this gradient disparity to modulate effective learning rate. And the way it works is this. So we keep track of the gradient disparities. On the server side, we keep track of these gradient disparities by doing a moving average. So then we get this D term. And then we compute the drift-aware effective learning rate by adding this moving average of the gradient disparity term, so that to achieve adaptivity. And then we assume that if the gradient disparity is going to be higher because of our drift happen, we can get a higher moving average. Because of the higher moving average, the drift-aware effective learning rate is going to be higher as well. And because of the higher learning rate, the client side can train the model so that it can adapt to the drift much faster. The main result for I show here is for incremental drift. So in incremental drift, we assume that like 20% of the clients will change their data distribution every 100 runs, starting at runs 2000. And we also showed so the x-axis are the number of the runs, and the y-axis are the validation accuracy on each of the clients, and different curve corresponding to different federated learning algorithm. We show that, so the purple one is the oracle. That means you have perfect knowledge on when the drift will happen. The blue line shows the flash. So we show that the flash can enable much faster recovery compared to the baselines. And also flash also has a chance to achieve higher accuracy even after the drift happened. The main takeaway from the work is we can use a server-side drift-aware adaptive optimizer to help combat with both data heterogeneity across device and also data heterogeneity across time. By keeping track of the gradient disparity, we can try to balance the stable training without drift or even with drift. So Flash are able to recover from our drift very quickly in roughly 60 rounds of federated learning training and achieve the least percentage of accuracy drop compared to the Oracle. So I'm very proud to say that all the work are built with flowers. And if you have any questions, this is the time to ask. Thank you very much.
So do we have questions in the room? We have one question down here. Payne will be there with you momentarily.
Hello, do you hear me?
Yes.
Great. So thank you very much for the presentation. It's pretty nice. I would like to know if this flash concept that you are introducing, have you done simulations to check if it works under any level of concept drift? Like you were mentioning that you were doing something like close to 10%, to 20% that it changes, but have you done more, let's say, simulations to check that it works under any level of concept drift?
Yes, so we have very extensive evaluations in the paper. We consider incremental drift, we consider sudden drift, we also considered like a recurrent drift, and then we consider different percentage of clients to have drift in the incremental setting as well. We show that Flash can give you the best performance in all those settings. We even considered even without drift at all, and Flash can give comparable accuracy with existing adaptive optimizer.
Okay, thank you.
Great. Any more questions here? How about online? Oh, sorry. Yes, there's a question just at the front. Thanks, Pan.
Hello. So my question is that, so the data can be heterogeneous across the clients because of different regions. And one of the region can be a dishonest client. So if a couple of dishonest clients are present, they will have a heterogeneous data. And so maybe my question is that how the global model will be impacted when we have a dishonest client?
So I didn't quite get the last sentence. So what will happen to the global model if a client has what?
Yeah, so how the accuracy of the global model will be impacted if we have a couple of dishonest clients having heterogeneous data?
Okay, so that is what will the performance of the global model if only a very small percentage of the clients has heterogeneous data? Is that the correct understanding of the question?
Yeah, a very small percentage of the clients are having heterogeneous data, but we do not know whether these clients are dishonest or they're having really out of distributed data.
Oh, I see your point. So I mean the clients who have decided. who have heterogeneous data could be they're not honest at all, or it could be even that they get under attack. So I think that's part of the benefits of doing personalization for the client. In this particular work, we didn't actually evaluate for adversarial attack setting. So the goal of this work, the goal of the flow, is to make sure that the global model is get trained in a way such that after it get personalized for each of the clients, they can get good performance on each of the clients. So all the clients has data sets that are different from each other. So you can think that all the clients in a way, you can think all the clients are dishonest. So all of their data distributions are different. In particular, we do the simulation with, in this particular example, we are using, so in this particular figure I shows, it uses a LSTM model and then try to do next word prediction. And we use the ready data set. So the ready data set, it's already inherently heterogeneous, so that every single client will have a different set of data sets and their distributions are actually different. So does that answer your question at all?
Sure, that's fine.
Yeah, he's nodding. I'm sorry, it's a little bit difficult when you're remote and you don't have a camera. I'm sorry for that. Charles, nothing? Well, actually, we're bang on time, so I'm going to close it here. And thanks again so much, Hui, for telling us about these two fantastic pieces of work. Thank you. Thanks so much.